Okay, second part of our lesson for today. This is over exponential models. It's going to be a lot like linear models, except instead of a linear function, we're going to introduce the idea of what we call an exponential function. So linear functions are a straight line that we're used to working with, but exponential functions are a little bit different, and they actually are a lot different. So you may have even heard of a thing called exponential growth, and that is a pattern of growth that can be modeled by an exponential function. Um, so our exponential functions look something like a times b raised to the x power, where x is our input. So this is why we would say this is an exponential function, because x is the exponent. Exponential. Yes. So there's only two values that we need to know here, and that would be A and B. Well, there's something about how exponents work that maybe can help us identify how much work we need to do to, at any given time, figure out what A and B are supposed to be. Well, we know that any number to the 0th power should just be 1. I say we know that. Everyone forgets that. It's okay if you didn't know that. But what I'm saying is that a times b to the 0, because b to the 0 is 1, should just be a times 1, which hopefully we know is just a. So a is genuinely the starting value, right? Because this is what I get when I plug in 0 to my function at the starting time, right? If this is some real life scenario, plugging in 0 is our initial value. So if I told you we had some exponential function where we start with some given value, an example that we see later is a little odd, but I think it's kind of cool. It is lead in your bones as you've been exposed to it. So lead is bad, but it stays in our system. It gets absorbed by our bones. And so there's a question later that is measuring the amount, grams of lead per bone, for like per gram of bone, um, or gram of lead per like body weight or something. I'm not sure. But it said, imagine you've been exposed, your body has absorbed 8 grams of lead. Then that is where you are starting. So that would be 8 would be your starting value, which immediately then tells you that that is a. So we have two values in exponential function. A, we get to say, is always going to be our starting value. A is our starting value whenever we plug in x, or whenever we plug in 0 for x. That is going to be this a out front. So we have an exponential function. Exponential. A is starting. And B is going, sorry, B is what we may call percent change. Now we have to be a little bit careful as far as the context of what. So percent change as a larger, more vague idea is a rate, not necessarily a rate of change, sorry, that's a bad word, is a percent of change as our outputs change. So we may write percent change, it's often given as f of x2 minus f of x1 over x1. I'm sorry, f of x1 at the bottom. And that would be the decimal form. So we make it a percent by, as always, just multiplying by 100%, right? Moving the decimals 2 places over and adding a percent sign. Um, so this is just a way of identifying where, how much our outputs are changing. So for instance, if for some reason I had an output of 0.5 after having an output of 0.25, then percent change is asking how much did we change going from 0.25 to 0.5? Well, that difference on the top is 0.25, and then divided by 0.25 is 100. So how much did we change from going from 0.25 to 5? 100%. We 0.25 plus how much of 0.25 is 0.5? 100%. And these are very weird ideas that we're articulating here, so it doesn't feel directly applicable, and that's because it almost isn't. But B, for an exponential function, does happen to be the percent change, and let's go into some specific real-life context for that. Imagine you have a loan with an interest rate of, let's say, 12%. Um, Instead of a loan, let's say it's a savings account or some kind of investment account that you're not touching whatsoever. So that would be your interest rate, would be your percent change. Well, so it's increasing the amount in your account by 12% every time it's checked. So that is, you take whatever number you started with, X, and that's a bad example. Let's say you started with $25. Then we want to add 12% of $25. Well, as a decimal, 12% is 0.12, right? So we want to add 12% of $25. And I'll erase the dollar sign. Um, but how do we write increasing by 12% as a single number? Well, I can factor a 25 out of both terms here, and this is 1 plus 0.12 times 25, which is a single decimal, sorry, 1 plus 0.12. And as a single decimal, this is 1.12 times 25. All I'm articulating here is that at a given year, if this is increasing by 12% every year, then we take 1.12 times 25 for the first year. Now, let's say we wanted to take this again after the second year. Well, the first year had a result of this value, 25 times 1.12. That's how much we had after the first year. Well, now to find the growth from the first year to the second year, we need to multiply again by 1.12. Well, now I'm multiplying by 1.12 twice. So I can actually write this as 1.12 squared. Well, let's say we wanted to find how much we would have after the third year. Again, we would do 25 times 1.12 times another 1.12. Sorry, there's two here. Well, now we're multiplying by 1.12 3 times. So I would do 25 times 1.12 raised to the third power. And so maybe we're seeing a pattern here. Our interest rate, or sorry, the amount of money in our account at a given time is actually given by the function 25 times 1.12 raised to the t power, where t is years after the initial investment, with 25 being the initial investment. And again, this was given by a 12% interest rate. So we were able to identify that this percent change, I erase those, I meant to underline. This percent change happening here was based on the interest rate that we started with. So with a 12% interest rate, this value for B is going to be 1.12. Now let's say instead that we had something that was decreasing by 0.12. Now, instead of being 112%, if we were decreasing, then at every point in the year, our change would be that we would be at 88%. That is, if you're losing 12%, you are left with 88%. So that would correspond to a function where instead of being 25 times 1.12 to the t, this would be a situation where it would be 25 times 0.88 to the t. And these are two different various scenarios, but it's just kind of helping us identify what that percent change is there. So all that to say, that's kind of how we can take a little bit of a word problem and figure out what those values should be from there. Now, let's say instead that it gave us a lot of points in a table, and we wanted to find an exponential function that fit that data given. Well, now we can do something that looks a lot like what we just did for our linear functions, but instead of being for linear functions, we are doing it for an exponential function. So let's share this and go to, yes, this value. So I'm going to be pulling the data from this table that is in our notes sheet for 1.5. So we go to the online calculator and I'm waiting for, there's a bar at the top that are the zoom tools that is covering up the tabs to click on. Okay, I'll just click on the button again. Okay. This is some online test thing with a graphing calculator built into it. So it's a really interesting approach to getting to a graphing calculator online. Anyway, so now we're back in this graphing calculator and I want to find a best fit function. So I need to put my data into a list. So I press stat. I want to edit my list. So I go to edit. And because this is a brand new calculator, it is empty with all the values. So I need to input all these different values. And the there we go. Now we go back to this chart. Wrong one. And our inputs are supposed to be 0, 1, 2, 3, 4. So let me put that in. 0 for the first one, 1, 2, 3, 4. And now for our y values, 1.72, 1.72, 0.63, and then 0.24, so 0.63, 0.24, 24. I did not get the 4. 0.24. Okay. 0.085, 0.085, and 0.032. 0.032. Okay, so now we have all of our data in a list, and we want to find the best fit function corresponding to this data. So we are going to go to the stat button, and we're trying to do calculus. So we go to the calculus section, and we are trying to find a regression model that is exponential. So we keep going down and we see EXP-REG, that stands for exponential regression. Regression, again, being the technique of finding a best fit function, and EXP standing for exponential. So we hit enter, highlighting that. Our X inputs are the first list, our Y outputs are the second list, and we are going to store this in one of our functions. So we go to VARS for our variables. We go to Y variables. We're wanting to store it in the function. So we go to function, and I want to store it in Y1. So there we go. And then we highlight calculate and hit enter. And boom, it tells us exactly what A and B are supposed to be. And now we can go to Y equals. And here we see it has stored those values in this function. Now, if we were writing this down, we remember that a complete model has coefficients, so the A and B, up to 3 decimal places of accuracy. Now, 3 decimal places of accuracy for this kind of function would mean we would look for 0.368 and then round out to this decimal, so it'd be 0.369. So we would write down 1.722 times 0.369 raised to the x power. So again, our calculator identified the best fit function corresponding to this data, and we can even look at the graph for this, and it looks like that. And there's even a way to get the points from our list graphed here, but trace. I do not remember how to do that, and it's not important. It's good to see. I'll try and have this figured out for class tomorrow so we can look at it. So yes, that is how we find an exponential graph or function given a set of data from an input. Okay. So now the next step that we may want to do is figure out some of the values from parts that it gives us. So imagine it said the half-life, I don't remember the phrasing of the problem. We're going to cover that tomorrow. So this is all we're going to talk about exponential for today. And tomorrow we're going to go finish what we're doing for exponentials and then start with the next kind of model that we are approaching. So again, so far we have linear models and exponential models. Both of them only require two variables that we look for, two coefficients to complete the model. Now, sometimes there is a very natural question of what kind of model do we think best fits the data that we have. And that is going to be when we want to look at the points, plot those points and kind of look at them and say, what graph do we think really fits this the best? And again, once we review how to plot points, we'll do that and then start asking those kinds of questions. So far, we only know linear and exponential, and we're going to compare those for this last function that we just came up with and try and justify to ourselves why we do or don't like the exponential model for this data. So that is all that I want to talk about exponential functions for right now. Tomorrow we're going to finish them and then get into the next type of model function. We're going to talk more examples about exponentials Because again, right now, I think the linear models maybe is really good to identify what kind of situations those are, but exponentials are something that come up a lot with a lot of varying different type of situations. So something like loan interest, um, really kind of any interest is happening, is an exponential model. So, yep, that's all I have for right now, and I will see y'all tomorrow. Goodbye. I pressed leave on the iPad before I actually just ended. I could have just ended the meeting. Okay, goodbye.